Okay, hello everyone. Thank you for joining us today and welcome to the second day of the TAPI Nano conference. So session 12 is about novel processing routes of nanocellulose-based composites. And our first speaker is Dr. Mehdi Tahbidi. He's an associate professor, from the University of Maine. So we will watch his presentation. If you have any question, you can type those on the chat, and then we will read them. And if we have time, we will have a Q and answer session at the end of his presentation.
Hello, everyone, and welcome to my presentation today as part of the TAPI Nano 2021 virtual conference. I really hope that 3 is a charm, and next year at least we can meet up again in person in Helsinki. My name is Mehdi Tahbidi. I'm the Associate Professor of Renewable Nanomaterials with the School of Forest Resources at the University of Maine. I also hold a cooperative faculty position with Advanced Structures and Composites Center, and also with the FBRI, Forest Bioproducts Research Institute at the University of Maine. I am a collaborating scientist with the Process Development Center at the same time. So today I'll be talking about a closed loop production of cellulose nanomaterials and products, new product development efforts that we are doing at the University of Maine. So we all know about the primary forest products production. And again, my background is primarily in wood science and technology. All these forest products normally have some mill residues and also forest residues that are left in the forest. The idea is that if you can produce cellulose nanomaterials, CNF, or lignin-contained nanocellulose, or CNF, LCNF, and then combine them with some traditional wood particles or wood elements, then you can develop new products that can actually be recovered and recycled at the end of their service life, and then close this circle. So I don't think this audience needs an explanation of nanocellulose and what we are talking about, but briefly, we talk about normally 2 main groups of nanocellulose, CNC, which is cellulose nanocrystals, and CNF, which is cellulose nanofibrils. Cellulose nanofibrils, that are the major area of concern today in my presentation, are more like a spaghetti-like structure, as you see here, whereas cellulose nanocrystals are more like rice-like structures. And if you have ever been to Maine, you know that Maine has a lot of fiber and also a lot of water. So no surprise that nanocellulose is important here because it's actually fiber in water. Over the years, there have been a lot of efforts to produce nanocellulose and find applications for this material. There is a wide range of applications, from cement to cosmetics and paint and as rheology modifiers, to coating, to composite materials, packaging material, drug delivery, and many, many more applications. But when you want to decide which direction to go, the big question is, what is the criteria to decide which direction I should actually go to? Considering everything, and we all love things being sustainable and renewable, but in the end of the day, it's actually the cost that is very important. So where it is closer to money is actually the best way to go to. But we all know that there is a lot of things that we should do so that we can get to that location. For any new product or material that comes into the market or wants to find some way into a market, there are one of these 2 options, I guess. One is to force it into something that it can't do and fail, or instead look at the strengths of the material itself, see what it can do, and try not to force it into what it can't do. There are some other considerations when it comes to cellulose nanomaterials in particular, is that, of course, the cost is important. We talk about the scales also. You know, in my previous academic life, I had worked with nanocellulose mostly in the small vials and small quantities and a higher price. When I came to the University of Maine, the scale was very different. We already had a nanocellulose production line that was at a capacity of a ton a day on dry basis. So the expectations were very different. The other thing that is also important is form. So nanocellulose is produced in water, and we all know that drying nanocellulose is not really so easy. On the right, you have a picture of our cellulose nano fibril production line at the scale of 1 ton on dry basis a day. And then I also have a picture here of our spray drying pilot scale production line, which basically is on the same scale, pilot scale, but it can only produce 1 kilogram a day of dry nanocellulose. So we can produce a ton a day, but you can only dry about a kilogram a day. So that gives you another idea that if you want to do something more economically feasible, you have to go through the skip through the drying process. So with that explanation, the research at my lab, which is called the Laboratory of Renewable Nanomaterials, or LEARN, is focused on several things. First of all, we want to look at what CNF is good at naturally. We don't want to force it into anything that it can't do. The other thing is that we want to really do our best to not to dry it unless we really have to, which basically means that we are producing our final product. The other thing that is really important is how to do this processing and produce a final product and still maintain the nanoscale dimensions of nanocellulose. So the difference between cellulose and nanocellulose is basically in that nanoscale thing. So if that nano is gone, which is mostly possible when you do other types of drying, you are actually losing all the benefits of the nano dimension. And we also are looking at large volume and lower value products, higher scale of production, and then we are trying to make CNF cheaper with different ways. So a few years ago, we had a question of what can we do to basically marry the two ends of the spectrum of the modern forest products in these days. So, you know, people are talking about tall buildings like CLT, cross-laminated timber, and also a nanocellulose. So it seems that the future of forest products industry is actually within this range. So we had the question was, how can we marry these two and produce some intermediate products that can actually take advantage of the nanoscale, but can be used in larger scale. So the question, as I showed you in the previous slide, was that can we use nanocellulose as a binder or an adhesive to replace other resins? The biggest issue for that actually is in water. So we know that nanocellulose is produced in water. In this case, there's a 3% solid CNF, and you have here wood particles, the same wood particles that are used to produce particle board. If you mix these two together at the ratio of 15% dry basis of this and 85% dry basis of the other one, you end up having a mixture of about 15% solids content. If you take a small amount of this nanocellulose in your hand and try to squeeze the water out, you can't do that. It holds tenaciously to water. It's very difficult to do that. So that is impossible to do. But when you mix these together, the magic actually happens naturally. And this process that we now have called contact dewatering basically enables that water, it is in the form of bound water, to change into free water, and then it can be easily mechanically removed from the system. So if you compress this mixture from 15% solid, you can get to about 50% solid content. If you do several times, you can even go to higher solid contents. And that will save a lot of energy. So I have a video here to quickly show you what we mean by contact dewatering. So here, I'm trying to basically press or squeeze a small amount of nanocellulose between inside the plastic film, just to put force on it and try to remove water from it. As you see, it is not possible to do that. Here, I'm adding a little bit of wood particles, larger pieces of wood particles to it, and then trying to do the same squeezing process and try to see if you can see any water coming out. As you see a little bit of water, it's being separated here on the side. It's not really that much, but you see there is something happening. Now, if you switch those larger particles with these smaller particles, the amount of nanocellulose is the same, the solid content is the same, the amount of wood is the same. The only difference is the particle size and therefore the surface area or a specific surface area of the wood particles. If you do this now and then do a similar thing and try to get the water out, voila, this is what we call contact dewatering. And you see that water is actually getting separated so easily, and this water actually doesn't have any nanocellulose in it. All the nanocellulose is stuck in the system. So we recently published this work, which basically shows you how fast it is possible to dry or dewater nanocellulose in the presence of wood particles. So this is the curve for 3% CNF, and then these other curves are for when you add wood particles to it with different particle sizes. When you go to smaller particle sizes or higher surface area, what actually changes is this instantaneous dewatering. As you see, from about 3.3 for 3% solid CNF and 0.66 for the 10% solid CNF, you get to values about 10 grams, which is much faster dewatering. And you can see that in the rate of dewatering also here. So having this enabling technology also means that you get the advantage of having nanoscale dimensions CNF here in the system. So this is the wood particle, and you dip it in nanocellulose, you dry it, you see nanoscale dimensions, and this is what you want. So we tried this on a larger scale. This is a trial to do a 3 by 3 feet panel production, the same way, mixing them together and then forming them into a form. And then you put this in a cold press to apply pressure. This mixture has about 60 pounds of water in it, and you do contact dewatering in a matter of about a minute or so. You get about 33 pounds of that water out. And this water basically doesn't have any nanocellulose in it. This is the first panel that we made, and this is the people who were all happy. A few months later, we decided to go larger. At the Advanced Structures and Composites Center at the University of Maine, we do have a 4 by 8 feet press. So we tried making a larger panel. This panel was made in the same way, dewatering. This is the dewatered panel, then goes into the press. And there you have, this is the largest particle board ever made using nanocellulose binder, 4 by 8 feet. It has about 15% by dry weight nanocellulose and 85% wood particles. In terms of mechanical and physical properties, it's at least as good or even better than regular particle board at lower densities and medium densities. This idea of enabling technology of contact dewatering also forced us to get into other products. This is a pilot scale production of wallboard or gypsum board. Gypsum boards are very common in North America, but these gypsum board replacements basically do not have any gypsum in them. They have that particle board in the core and the paper lining on both sides. This line shows the mechanical properties of the gypsum board, and we can get much better than that at a lower density. We are still working on the fire resistance, but initial test results have been promising. This is the one that we have developed, and this is the regular gypsum board. So one big question here is how fine your nanocellulose should be so that it can do the bonding for you. We know that nanocellulose, as it is produced at the PDC at the University of Maine, is basically a mechanical process where you put cellulose and water in, and you apply energy, and you get your nanocellulose. The regular nanocellulose is produced at 90% fines, but you can produce it at any fines content that you want, and you know that if you go further, you need more energy. And also, there is another way to reduce the cost of nanocellulose is to go from bleached kraft pulp to something like OCC fiber, which is much cheaper. So we did the same thing. We produced CNF from bleached kraft pulp and LCNF, lignin-containing nanocellulose, from unbleached kraft pulp. We checked their density of the films and the tensile modulus and tensile strength of the films. What we saw was that in many cases, we actually see that the properties kind of level up at around 70 to 80% fines content. So basically for our properties, and in addition, if you do these shear strength tests or lab shear tests, you can also get an idea of the bonding properties, and they also kind of level up at about 70% fines. So the conclusion is that for these applications that we are concerned about, we really do not need to go that high fines content. And again, as you know, the difference in energy consumption is actually very, very much. So if you go with LCNF and you go with smaller fine content, you get the similar bonding properties and you can still save on energy. So I want to just take a moment to introduce some other applications of this. These are basically interior wall coverings, molded shapes. This is a styrofoam packaging application, which there will be another presentation from University of Maine later on today, more discussing about this technology. And I want to just finish the presentation with this note that for many new product development and everything around innovation, we are advised to look outside the box. In the case of nanocellulose, I really think that the answer is actually inside the box. Thanks very much. And I would like to thank my team and the funding agencies that supported this project. I'll be happy to answer any questions if there are any. And thanks again.
Well, thank you, Mehdi, for the presentation. It's super interesting. So do we have any question? We have one on the chat. They are asking, have you looked at surface modification of the CNF to improve its flame retardancy?
Very good question. Thank you for asking that, Mark. No, we haven't looked at the surface modification for that purpose. We are looking at it as a way to change our dewatering system. But whatever that we will be doing should be done both to the CNF and also the wood particle part, because again, in these formulations, the major part still is wood. So whatever technology is out there for wood fire retardancy can be applicable here too.
Thank you. We have another question. Dr. Tafidi, very interesting presentation. I'm wondering, how does the CNF compares to urea resin fireboard?
Yeah, in these experiments, we did not compare directly with the urea formaldehyde-based formulations, but we use the ANSI standard values. So there are minimum standard values based on ANSI standard. I think it's 208. And then our properties, again, there are several density levels. At lower density and medium density, we are at or above. For high density particle board comparisons, we are not yet there.
We have another, David say thanks. Any feeling for the characteristics required in the contact dewatering material?
For now, we know that the contact dewatering material should be preferably porous and hydrophilic. And if these two things are there, it is possible to do that. So we are doing this contact dewatering with many other types of materials these days.
Do we have any other question? If you want to turn on your microphones, you can also ask. I have actually one question. The results that you show with the bleach CNF, that bleach CNF was produced without any chemical treatment or any enzymatical treatment. It was just a cellulose pulp that you mechanically treat?
Yeah, the starting material is bleached kraft pulp. So there is some chemistry before we get it, but after we make it into nanocellulose or during that process, no, there is nothing chemically done on that.
Okay. And have you tried, for example, from different sources like softwood versus hardwood, how that affect the properties of the boards?
No, not yet. We are using our standard, what we call the 90% fines CNF. That was at the beginning. And then when we were looking at the effect of fines content, we used the same starting material, but just refined it to different levels. But no, the source of fiber was still the same.
Okay, thank you. So we have 1 more minute for questions. Okay, so let's move with our next speaker. Our next speaker is Dr. Natalia Herrera. She's a researcher at the Department of Aeronautics at Imperial College of London. So let's watch her presentation, and if you have any question, you can type them on the chat or use your microphone at the end of the presentation.
Okay, so we are ready to start. My name is Natalia Herrera. Today I will talk about high impact strength composites based on impact modified acrylic and bacterial cellulose. I work as a research associate with Dr. Kunyan Lee at the Department of Aeronautics at Imperial College London. Today I will mention what is bacterial cellulose, the motivation of this study, the materials and the methods, the properties of the PEG-sized BC nanopapers, the properties of PEG-sized BC reinforced laminate acrylic composites, and finally the conclusion. So what is bacterial cellulose? Bacterial cellulose is produced from a bacteria that when it's filled with sugar, as a result, it produces the glucose molecules, and these glucose molecules produce cellulose chains. The cellulose chains together, they form small fibrils with a really small size in nanometers, and these fibrils come together to form the nanofibers of approximately 50 nanometers. The nanofibers grow together, forming a network, and it looks like this image in the right under the microscope. And the visual appearance of bacterial cellulose is like a jelly-like 3D fibers network. Bacterial cellulose is commercially available and it's not like a nata de coco, and it's also chemically pure. It has high crystallinity, approximately 90%, and the BC single fiber shows a modulus of 114 gigapascals. When bacterial cellulose is wet, it contains approximately 99% of water, and it's not like a BC pellicle. This BC pellicle, when it's dry, is formed as BC nanopaper that is a two-dimensional network. The question is, can we reverse this process and reheat the dry BC? And the answer is not, because there is a process that is called hornification, that when you dry cellulose, there is a formation of irreversible strong hydrogen bonds between the adjacent fibers. And due to this hornification process, the BC nanopaper presents high mechanical performance with a modulus of 20 gigapascals, a tensile strength of 188 megapascals, and with a strain of 1.4%. For this reason, these bacterial cellulose nanopapers have been used as reinforcement material for different types of matrices. In our group, in a previous study, neat PMMA was reinforced with dry BC with one layer, and it was found that the impact strength of PMMA was increased approximately 20% using one layer of BC. But let's point out something here. The strain of dry BC nanopaper is really low, 1.4%, when we compare with commercial polymers, like in the case of polypropylene, that is 20%. So the question is, if the strain and toughness of the BC is improved, can that be reflected in the impact strength of the composite? So there are two questions in this study. The first one is, could the interfibril hornification be circumvented to enhance the toughness of the BC nanopaper? And the second question is, could the toughened BC nanopaper be translated to improve the impact strength of BC composites? So we will find out the answer during this study. So the materials that were used, because the matrix is the commercially available impact modified acrylic. We have an example here in the picture. This is the transparent material with the highest impact resistance that is currently available in the market, which makes that the goal of this study is high. As reinforcement, we use bacterial cellulose nanopapers. The chemicals used were polyethylene glycol with 3 different molecular weights, triethyl citrate as a plasticizer, and the monomer and initiator. These last three chemicals were used to produce TEG plasticized PMMA syrup, which was used like the interlayer adhesive to glue this panel of IM acrylic together with the CV nanopapers. So the methods we have as a first step the sizing of the VC with the PEG to produce the PEG-sized VC nanopaper. I show here a schematic representation of the process. The wet VC pellicle, never dry, was immersed in the liquid PEG, the three different PEGs, and then after that was pre-dry in an oven with a slow process to remove the most amount of water possible. After that is come the consolidation process in a hot press for 30 minutes. As a result, we have cellulose nanopapers, as you can see in the image in the presentation, which has an average of 50% PEG in weight. These nanopapers are dry and they don't show any wet film. In the second case, we have the preparation of laminate acrylic composites reinforced with the produced VC nanopapers. Here I show the representation of the process, and as I mentioned before, the first step was to produce the text plasticized PMMA0 used as an interlayer adhesive, and that was pre-polymerized in a water bath for 30 minutes at 70 degrees. After having the syrup in a specific viscosity, it was poured in the acrylic panel. On the top of the syrup, it was placed the VC nanopaper, and on the top of the VC nanopaper, it was poured again more syrup of the text plasticized PMMA. Finally, it was everything sandwiched with a second acrylic panel, and all the set was placed in the oven for 4 hours at 70 degrees to further finalize the polymerization of the text plasticized PMMA interlayer. As a result, we obtain laminate composites with 0.2% of cellulose, and they have a layer structure as is shown here in the picture. And then we have the visual appearance of the composites. Now we will move further to the VC and PEG-sized VC nanopapers properties. The first one is the tensile properties of these nanopapers. We have the curve strain curve, and then we have a neat VC in the red curve with approximately 170 megapascal of strain and 16 gigapascal of modulus. As it was expected with the incorporation of PEG, the strain and the modulus were reduced. But as I mentioned before, here we are focusing in improve the strain and the toughness of this VC nanopaper. So with the incorporation of PEG, we can see that the neat VC with a strain of 3%, it was further increased 5 times to beyond 50% of a strain. And the work factor of the neat VC was measured with like the area under the curve, and it was found that the work factor of neat VC is about 3.8 megajoules per square meter, and that it was further improved up to 14 megajoules per cube meter. And this improvement in the work factor means 270% of improvement, which is high improvement. So the second property was the fracture toughness of this VC nanopapers. The first curve we have is the load against this displacement. The red curve for the neat VC shows that as soon as we reach the maximum load, the material fails in a catastrophic way. However, in the PEG-sized VC nanopapers, we can see when we reach the maximum load, the crack propagate in a stable way. So the normalized K1C was measured, and the neat VC show at 10.6 megapascal per square root meter, and then the other materials has lower values. In the case of the resistance R curve, what we will measure is the further resistance of the crack to grow. And in the case of the neat VC, there is a flat curve, and that means that while the crack is propagating, there is no need, there is no further resistance of the material for the crack to grow, because that resistance is constant. However, in the case of the PEG-sized VC nanopapers, every time that while the crack is propagating, there is a further resistance to be overcome to be able to the crack to propagate. And that is because the plastic zone in the tip of the crack for the PEG sizes PC nanopaper has increased the size, so it will require more energy dissipation to be able to get the crack to keep propagating. And that is the reason that we have this rising arc curve for the PEG sizes PC nanopapers. And this plastic deformation is observed under the SDN images that we can see here. We can clearly see that in the BC, this is the direction of the crack propagation, and the BC, there is not a clear plastic deformation observed. However, in the other nanopapers with PEG, we can clearly see that there was a plastic deformation, which means that we need more, there was more energy dissipation in these materials. Now we will move for the properties of the BC reinforced laminate acrylic composite. So the first one is the tensile properties of the composite. So we have a tensile modulus for the neat acrylic that is around 2 gigapascals. And as we can see from this curve, there is not a significant impact on the modulus when the composites were produced. Regarding the tensile strength, the composite, the neat acrylic and the acrylic, two acrylics that were glued with the TEC PMMA interlayer, they have a tensile strength of approximately 47 megapascal. That is similar, and the interlayer, PMMA interlayer didn't affect this tensile strength. However, when we add the BC to the system, it can see that it will decrease the tensile strength to a value of approximately 35 megapascals. That is because, as we remember or we saw earlier, the BC fails quite early because it fails at 3% of strain. And that makes that the tensile strength is lower because the composite fails when the BC fails. And in the same way as the BCs with the PEG, they fail at much larger strengths. Therefore, the tensile strength in the composite becomes again a bit higher, and it becomes to values around 42, 43 megapascal, which is still not significantly different to the 47 megapascals of the neat acrylic, which means that there is not a big impact on the tensile properties of the acrylic composites when we introduce these BC nanopapers. And if we move forward to the Sharpie impart strength properties of the composites, we will look first at the acrylic, neat acrylic, and the acrylic with the TEC PMMA interlayer. They have really similar impact strength, around 11.5 kilojoules per square meter, and this value was increased to 18 kilojoules per square meter when we add BC. This means a 50% increase in the impact resistance of the already impact modified acrylic. So what happens when we add PEG 100 and PEG 600? It will be further increase of this value to 26 kilojoules per square meter. And that means that it's 120% improvement in the resistance of the impact modified acrylic. But when we look what happened with the composite containing the PEG 200 nanopaper, we see that there was not further improvement. And the question is why? To understand this, the contact angle between the interlayer in a thin film form was measured with the liquid PEGs. And it was found that the contact angle of the PEG 200 was much lower than the contact angle of the PEG 400 and 600 with this interlayer adhesive. And there is not a big difference between the PEG 400 and 600. So when there is a lower contact angle, it will mean that there will be larger interactions on the interface, and that can lead to a stronger interface. When there is a stronger interface in a system, what it will happen is that the crack will penetrate the interface, and it will keep going to the BC200 paper in this case, because the crack propagates through the pathway of lead resistances. So it will just pass through the interface and it will not propagate through the interface. And in this case, it will go directly to the nanopaper and it will be debonding on the BC nanopaper. In the case of the system, in the case of the 400 and 600, that the interface is weaker. So what happens is when the crack arrives to the interface, it will be debonded in the interface because the crack will propagate to the easy way, and then it will branch, and then it will penetrate to the paper. And then in this case, or in this system, there is interface debonding plus debonding of the BC nanopaper, which just means there is extra energy absorbing mechanism. That will explain the results of the higher impact strength of the composite containing the PEC 400 and 600 BC nanopapers. As a conclusion, we can say first that the sizing of never dry BC pelican with PEC improves the BC nanopaper toughness by 270%. And a second conclusion, we said that the low load fraction of bacterial cellulose, 0.2% in weight, increased significantly the impact strength of commercial impact modified acrylic by 120%. Finally, these improvements, which are high, are obtained with a simple method, making BC paper, sizing in the BC paper with PEG, and following a simple lamination process to prepare the composites. Thank you for your attention, and if you have any question, I will be happy to answer all of them.
Thank you, Dr. Herrera, for that nice presentation. So we have 3 minutes for questions.
Hello, thank you.
Hello.
Okay. I will be happy to answer them.
We have one question on the chat. They say, very interesting presentation. What testing was performed to determine mold and fracture toughness? I guess that's the question.
It's the single edge samples, the CENT, single edge notch samples, yeah.
Okay.
With one crack, pre-crack.
We have another question. Hi, Natalia. Thanks for this really extensive work. Have you performed any trials regarding recyclability or biodegradability when adding the PEG?
No, not really. I think we haven't focused in that part with this type of materials. The focus was more to improve the impact strength of the already impact modified acrylic, but we haven't focused in that part.
Thank you. I have a question. Are you thinking on any application, any particular application that you are planning already on using these films?
No, that we are planning to use them, no, but of course, any application that implies like a impact resistant, high impact resistant, it will be like a shield protection, for example, or any type of Windows panels that require this kind of impact resistance. So that will be the main application for it.
Okay, thank you. So we have 2 more minutes for questions. If you have any question, please type them on the chat or turn on your microphones. There we have another one. Did you compare the fracture toughness at different conditions, higher temperature and relative humidity?
No, not really. We haven't done that. We have done all the tests in normal conditions, like a humidity and room temperature. Approximately 40% humidity and approximately 20-25 degrees temperature.
Well, we have 1 more minute. Let's wait to see if someone else has another question. Okay, it seems that there are no questions. So I want to thank you to all of you for participating on this session. Make sure that you go and check on the other sessions. There are really nice presentations. And thank you. And hopefully next year we will be able to see each other live and not in virtual.